Have you ever just looked around and wondered why things are made the way they are? Why a specific material gets chosen for a specific job? Well, it turns out there's this kind of invisible blueprint, a whole set of physical rules that engineers use to build, well, everything. And today, we're going to start uncovering it. So let's kick things off with a simple one. You're in a room, you touch a metal doorknob, and then you touch a plastic light switch right next to it. The metal feels way colder, right? But here's the thing, they're both the exact same temperature. So what is going on there? Or how about this one? We literally trust our lives to an aluminum tube flying thousands of feet in the air, but you would never want an aluminum handle on a hot frying pan. Nope, that handle is made of plastic. What's the logic behind that decision? And hey, isn't just about everyday stuff. If you look at high-speed machinery, really advanced tech, you see traditional metals getting swapped out for things like ceramics and composites all the time. There are some really powerful reasons for these changes. You see, none of these are random choices. Not at all. They're all based on this fascinating and sometimes surprising set of physical properties. So let's go ahead and pull back the curtain and really dig into the science that decides why materials work the way they do. All right, first up, we've got to talk about one of the absolute biggest challenges in all of engineering, this constant battle between strength and weight. I mean, you need things to be tough, you need them to be durable, but for anything that has to move, think a car or a plane, it also has to be incredibly light. And the starting point for all of this is a property you probably remember from school, density. All it really means is how much stuff is packed into a certain amount of space. It's why a block of lead feels so much heavier than a block of wood that's the exact same size. But here's the catch. Being super strong isn't the whole story. An airplane made of the strongest stuff in the world is useless if it's too heavy to get off the ground. What really matters is the strength-to-weight ratio, or as engineers call it, specific strength. That is the magic metric. And just look at this. You can see the champions of this game right here. Titanium and aluminum alloys just soar above many of the traditional steels. And that right there, that's precisely why they are the rock stars of the aerospace industry. They give you all that incredible strength without the massive weight penalty. Okay, so we've talked about strength, but let's shift gears to another critical factor, heat. How materials deal with temperature is just as important. And it doesn't matter if we're talking about a cutting-edge jet engine or, just the stuff in your kitchen. And this actually brings us right back to our cookware puzzle. The metal pan itself, it needs high thermal conductivity. It has to move heat from the stove to your food as fast as possible. But the plastic handle, it needs the complete opposite, low conductivity. That's what makes it an insulator, and that's why you can grab it without burning your hand. But heat does more than just move through things. It also makes them expand. And when you have really rapid temperature changes, that expansion, working together with conductivity, can create these really powerful internal forces. We call them thermal stresses. And those stresses can lead to something called thermal shock. Just imagine pouring ice-cold water on a piping hot glass dish. The surface tries to shrink instantly, but the inside is still hot and expanded. That incredible tension can literally cause it to shatter. Well, the same thing happens in high-performance tools and dies, where it gets the name heat checking. So far, we've talked about properties that are kind of passive, right? But some materials are way more active. They can respond to things like electricity and magnetism in ways that seem, well, almost magical. We actually call them smart materials. And one of the coolest examples of this has to be the piezoelectricity effect. Think of it like a two-way street. If you squeeze or bend one of these materials, it generates a little electric pulse. But, and this is the cool part, if you send an electric pulse to it, it physically changes its shape. And get this, you use this effect all the time, probably without ever realizing it. That sensor that tells your car's airbag to deploy, it uses the force of the impact to generate a current. The head of an inkjet printer, it uses tiny electrical pulses to make the material flex and literally push out a single drop of ink. It's this amazing invisible magic hiding in plain sight. Okay, so materials need to be strong, they need to be smart, but they also have to last. And one of their biggest, most relentless enemies is the slow, steady attack of corrosion. And we are not talking about a small problem here. The direct cost of corrosion is absolutely staggering. We're talking hundreds of billions of dollars every single year in the US alone. It's this constant, expensive battle to keep our bridges, our ships, and our infrastructure from literally rusting away. But nature can be pretty clever. Some metals, the ones you'd think would be the most vulnerable, have actually evolved their own incredible, built-in defense mechanism.
It's a process called passivation. Take aluminum, for example. The split second a fresh aluminum surface hits the air, it instantly forms this microscopic yet unbelievably tough layer of aluminum oxide. This invisible shield is so good that it completely seals the metal underneath from any more attacks. It basically rusts just a tiny, tiny bit to protect itself from ever rusting again. How cool is that?
All right, so we've hit on strength, heat, electricity, and durability. Let's try to tie this all together by looking at something that seems incredibly simple but is actually super complex: a coin. Seriously, designing a modern coin is a total masterclass in material science. It has to meet this huge list of demands, and pretty much every single property we've talked about today comes into play. Let's just quickly break down this blueprint. For it to last a long time in your pocket, you need incredible corrosion and wear resistance. For a vending machine to recognize it, it needs a super specific electrical conductivity and density. Even the way it feels in your hand, that's a function of density. And every single one of these choices is a careful trade-off against all the others. And, of course, how much it costs to actually make the thing. So here's the bottom line, the crucial point of all this. Materials are never, ever chosen by accident. Every single object around you, from a massive jet engine to a tiny penny, represents a whole story of deliberate choices, a careful balancing act between dozens of competing physical properties. The entire world is really built on this invisible blueprint of properties. But now that you know how to see it, what are you going to notice? Why is your phone case made of that exact material? Or your coffee mug? Your glasses? The choices are everywhere, and now they're just waiting for you to discover them.